that will evolve over time of that interaction region, and we'll be able to understand what the shielding, how the shielding works and what it looks like. Next slide, please. But we're not alone in having something like a heliosphere. These are pictures of astrospheres. This is what it looks like around other stars, these bright interactions. You can see shocks, bow shocks out in front of them. You can see their astropauses. Now, you can't see that around our own sun because it's not bright enough. The interaction is not strong enough here for our own sun, but it is around some of these other stars. So we had to invent an entirely new way to measure these particles coming in order to take pictures of the boundaries of our heliosphere. Next slide, please. And so we do that through something I call energetic neutral atom imaging astronomy, ENA astronomy. Next slide, please. So what you're going to see here now is the expansion of the solar wind going out all directions. This is the solar wind flowing out past all of the planets, out to the boundaries, an individual particle, an individual hydrogen going out to the boundary. It gets out there, and once it gets out there, next slide, please. What you'll see is that it's possible for it to grab an electron from another atom that's floating through the heliosphere. Start the next movie, please. And so it's gyrating around the local magnetic field, and every now and then it encounters a neutral atom coming in from interstellar space. When it does that, it can grab an electron and go zipping off any given direction, and some tiny fraction come in all the way past all the planets, all the way past the Earth, and into one of our instruments at L1 on the IMAP mission, what I like to call a 10 billion mile hole in one. There. And when that happens, we make a measurement of that individual particle. And you measure enough of those particles, you can make this inside-out image so that you're sitting in the middle and looking out in all directions around you, and you see what it looks like, how many of these neutral atoms are coming in. And they tell you, and they're different energies, so you're able to do very precise imaging with them as a function of energy. You're able to tell what the plasma environment is like out at that interaction region. Next slide, please. We also do space weather and particle acceleration. This shows an example of a flare and a coronal mass ejection coming off from the sun. It drives a bow shock. It accelerates particles to very, very high energies. We measure those locally in situ with the IMAP mission as they go past L1 and they go past the Earth. And then actually some of those same particles that didn't come into our spacecraft and get measured directly but passed right close to our spacecraft, they continue to go out, and a couple, 2 to 3 years later, they can go out, have the interaction I just described through charge exchange, and come back in as energetic neutral atoms. So we see the whole life cycle of these particles. We see them coming out from the sun, getting energized very locally, passing out, and coming back in from the outer heliosphere and the outer heliosphere boundaries. That's a really incredible, exciting mission where we're able to do the entire life cycle of these particles and understand, I think, for the first time, sort of the holistic view of how this sort of region of space around us, our solar neighborhood, really works. Next slide, please. And so that's it. That's IMAP in a nutshell. It's going to be a fabulous mission. We are really looking forward to launching in 2 days and getting out there and doing this wonderful science and this very important space weather. Laura, over to you.
Thanks so much, Dave. My name's Laura Waldrop. I'm the principal investigator of the Carruthers Geocorona Observatory. And this mission is really investigating not just a frontier in science, but a literal frontier of our planet. And that's the outermost atmospheric region known as the exosphere. Next slide, please. So many of you are probably familiar with the lower atmosphere, which forms very well-defined atmospheric layers. This is, of course, where our weather happens. It's also where our airplanes fly. And in fact, it's where many of our low Earth orbiting satellites live. Now, right in that low Earth orbit is where the exosphere begins. But unlike the lower atmospheric layers, which are relatively well confined to our planet, they're held very close, gravitationally bound, the exosphere extends almost halfway to the moon. Maybe. And I say maybe because we don't know exactly how big it is. We don't know how many hydrogen atoms populate it. We know that only hydrogen is light enough to make it up to those altitudes, but we don't know whether they have spherical symmetry around the planet, or maybe the region is shaped like an oval, aligned along the Sun-Earth axis. Maybe it's got dawn-dusk asymmetries. We literally don't know because it's so big, it's very, very difficult to make comprehensive measurements of its properties. One of the best ways to observe the exosphere is through what's called remote sensing. where you, instead of taking a sensor and trying to directly measure the hydrogen atoms that comprise the exosphere, directly measuring themselves, this region is huge. You would need a gigantic constellation of sensors to do that. Instead, we look at the light that it gives off when the sun shines on it. And this light is in the ultraviolet, and it's what George Carruthers, the namesake of our mission, coined the geocorona. Next slide, please. So Dr. George Carruthers was a 3-time University of Illinois alum. We're very proud of him for that here at Illinois. But he invented the very first camera that was able to take an image of this exospheric, ultraviolet exospheric light, the geocorona. And it was deployed by Apollo 16 astronauts on the surface of the moon. The camera itself remains there to this day. What they brought home was the film canister. And you can see a picture of George Carruthers here holding that canister. And when he analyzed the images, what he saw was something incredible, which is that the exosphere extended beyond even the image that was able to be seen from lunar surface. This is 60 Earth radii away. So you need to get even further than that in order to see the exosphere in a single image. And that's exactly what the Carruthers Geocorona Observatory is going to do. Now, one image or a few images that have been acquired over the years, as I mentioned, there's a significant knowledge gap. It turns out this knowledge gap has critical significance for our ability to understand Earth's recovery from geomagnetic storms in particular. So this exospheric region, it's true, there's not very many hydrogen atoms up there, but the way that they interact with the near space environment controls, to a large extent, how fast Earth recovers from these geomagnetic storms. So because these interactions between exospheric hydrogen atoms and this near space environment, they dissipate that storm's energy,